So we are talking today. I just did the thing again. If you watch all of my videos from like lecture, the first thing that happens in every video is me going so, and like I just did it again, so it's on this one too. Today we're going to talk about the harmonic oscillator. I'm planning on talking for about 40 minutes, and then the rest of the time we'll be like dealing with the quiz thing. The harmonic oscillator is an interesting problem. So we spent the last few weeks, the last 2 weeks, generating our kind of base ideas of quantum mechanics and the simple problem, some of the problems we can approach, looking at just a particle moving translational motion. And that's been almost everything we've been doing has been with no potential energy associated with it. And we finally want to start talking about this idea of a harmonic oscillator. There's a lot of different things that people use to describe a harmonic oscillator, or you can use the harmonic oscillator to describe. Pendulum motion follows this harmonic kind of thing. Springs follow that harmonic thing. That's the typical example people use. The one that's important to us, the reason we're talking about it in the chemistry class, is it turns out that bonds also can act like a harmonic oscillator. Essentially, anything that has a restorative force, if I disturb it by pulling two things away from each other, they pull back towards each other. If I push two things towards each other, they push back away from each other. Right? It's restorative in both directions. If I stretch it, it's got some normal distance that it likes to sit. If I stretch it away or push it towards, it kind of has that bounce. For that reason, we can kind of predict that the potential energy we're going to look at is going to have some x squared term. Because whether I'm doing like a positive change or a negative change, I want it to have some force associated with it. Now the setup for the problem, there's a couple. I left this space here intentionally because there's some other parts we have to put in there. The setup for this, if we're doing our simple starting kind of thinking about it, we'll start with just a spring. And then again, this idea of a spring or a harmonic oscillator or a pendulum or a bond all kind of follow the same model. I've got some spring attached to some mass. This spring has a constant associated with it. The spring has that's our spring constant. It's essentially a restorative force. I put spring in quotes because it's a spring constant. It's the amount of restorative force, right? That can be how strong is the bond, how strong is the spring, how wide is the pendulum swing, all of those different ideas. This means our potential is going to depend, like how much this force happens. If it's got this normal length L naught, and we displace it to some length L, we're really not going to worry about this displacement idea. We're going to define this displacement as just x equals L minus L naught. So how much we displace, this difference, tells us how much the force is going to respond. If the spring constant is larger, we have stronger response. If the spring constant is lower, we have less response. So it's going to depend linearly on this kf. And we also end up with 1/2 out front. The 1/2 out front has to do with total energy arguments. But this is, for us, this is the potential energy for a spring harmonic oscillator. This is in classical terms, right? This is how we do it classically. If we wanted to do this quantum mechanically, we just turn this v into a v hat. We turn this x squared into an x hat squared. And now it's our quantum operator for harmonic oscillation. Our Schrodinger equation, our total energy now, which is kinetic energy operation plus potential energy operation, we now actually have some potential energy term here. So our Hamiltonian ends up being a 1/2m p x hat squared plus a 1/2 k x hat squared. Or if I plug in our definition for px, this would be a negative h bar squared over 2m
d by dx squared plus 1/2 kx squared. Putting subscript f on this because it's a k force. It's not the k we were using in the particle in a box. This is not random constant. This is a force constant for the spring. So now, after we define the problem, so if you remember, I think it was the first day, maybe it was the second day of class, I said the way that we go about our problems in quantum mechanics always follow the same kind of pattern. We start with defining our system. So we said, hey, we did linear motion. What else can we do? Let's do this spring type motion, this harmonic motion. We define our Hamiltonian. So that's setting up our problem. This is going to have boundary conditions. The boundary conditions we set up for this negative infinity to positive infinity. We can kind of imagine this going any distance away. Not physically realistic, of course, right? You can't take a spring and stretch it out to positive infinity. You can't take a spring and crunch it down to negative infinity. But this gives us, like the spring has a certain length to it, but this gives us the extremes. And we'll look at what limitations we run into inside of this as well. But that's the theoretical limits, right? We can go positive infinity to negative infinity. After we have our problem defined, we're going to use an eigenvalue problem to find the wave functions. Then we use those wave functions in the Hamiltonian to find the energy, which we kind of do when we're finding the eigenfunctions. After we find the energy and the wave functions, we can start asking questions about average momentum, average position, all of that. But we start with saying, okay, let's actually solve this when we set it up. So I'm going to go ahead and say we've got some h at psi equals e psi. We always start with the same type of idea. We don't know what the psi's are yet. Part of what we have to do is determine what the psi's are. This is going to end up being negative h bar squared over 2m d by dx squared psi plus 1/2 kx squared psi equals e psi. This is the equation we have to solve. And it turns out it's really hard to solve. So we're not going to solve it in this class. I will tell you, I went down an accidental rabbit hole for like 2 hours last night being like, but how do you solve it? We don't need to solve it. But what I want to point out, and part of why I'm glad I did that, is there are some considerations we can make to make sense of the general structure of what the answer is going to look like. We want something that when we take the second derivative, we end up with an x squared. So something when we take the first derivative, we end up with an x. We take the derivative again, we get another x. And so the type of function we might think of for that is something like e to the minus x squared. Right? If we take the first derivative, we're going to get a negative x over 2. Take the second derivative, we're going to get a positive x squared. So that kind of fits with these two parts. This energy term, that's going to have some other bit to it. Maybe there's a constant associated with this as well. Where am I looking? There we go. Maybe there's some constant associated with this as well, because it's not just always x. You can see there's some other variables out there. So we might need to modify this. But generally, this is a Gaussian function. This is something like a Gaussian function. Gaussian functions are really nice. It turns out we see them a lot in quantum mechanics, physics, chemistry, distributions. Gaussian functions work out really well. The fact that it's e to the negative x squared means as you go to positive infinity, you're going to get e to the negative infinity, which is going to be 0. As you go to negative infinity, you get negative infinity squared, which is just e to the negative infinity is still 0. So that means these Gaussian functions follow one of the properties that's really important for our wave functions. It's finite, right? As we go like positive infinity, negative infinity, it always crashes out to 0. It also turns out these are always single valued. That's another one of the things we like to have. Continuous and smooth, right? Those are the 4 things we look for in our wave functions. This chunk always has that. Now, this gives us the form of what a first answer would look like. Of course, we're going to need some normalization constant with this as well. And then, after we have our normalization constant in some first answer, this is where it gets weird. There's like subsequent possible answers, right? And that's where we start to get these funny functions called Hermite polynomials. You notice block H, not script H. No hat on it. There's some set of polynomials that works for solving this. Guess how this mathematician found them? Taylor series expansions, right? You know, so you look at this problem and say, okay, I want to find things that work once, work twice, work 3 times. You just keep expanding your answer and seeing which expanded answers work, which terms work out. This is a normalization constant. If I put this all into terms, this is our general thinking about it. If I put it into terms where I've got this h bar squared over 2m, this 1/2 k, I forgot my f again, kf x squared, it turns out that there's 2 parameters we define to simplify all of these things. One of those parameters this is the oscillation constant. This is essentially how quickly it's going to vibrate, how often it makes a oscillation, right? It's related to the spring constant and the mass. It's a square root of that. This is going to be one of those parameters that comes in handy. We've got our k, we've got our m. There's a lot of rearrangement. This is where I went down a rabbit hole for like an hour and a half, 2.5 hours. It was tracking all of the ways that people rewrite these constants. Because it turns out, the book I learned quantum mechanics from, that I still reference when I'm prepping for class, defines everything differently than the textbook we're using defines things. And it was a total headache for me to figure out how they related to each other. And it was mostly this second parameter. Everyone does this omega. This is the same omega for everyone. But the second parameter, I'm going to do it the way your textbook does, since that's the textbook you have. A little bit different. There's this alpha to the 4th term. And I couldn't figure out, like, the rabbit hole was y to the 4th. Eventually I figured it out, and I'll show you why it ends up being alpha to the 4th. But this alpha to the 4th term is equal to h bar squared over m k. And you can kind of see where this is coming from, right? If I multiply this over, I'm going to have this h bar squared over related to this kf term. I'm going to have this 2m, these 2's are going to cancel, that m is going to be next to that kf term. So this alpha to the 4th term is going to end up in the equation someplace. There's ways we can rewrite these different parameters to make it so they relate to this more. Like, I can rewrite h bar squared over 2m. So I can write h bar squared over m just by having kf alpha to the 4th. I can rewrite kf as having h bar squared over m alpha to the 4th, and I can plug these things back and forth, rearrange the equations in all these different ways that we don't have to do. But I did for 2 hours for some reason last night. And that gets us to more details on what this wave function is really going to look like. So I'm going to call it psi for the harmonic oscillator. That's h dot o. With position x. Yes, we'll do it this way. Is going to be equal to our normalization constant times our Hermite polynomials, where we've got, I should actually call this psi v. Sorry. Just like we had, we had psi n's when we were doing the particle in a box, and n was our counting number. The boundary conditions of how this thing behaves, we end up with a counting number. To make it so we don't get too many like subscript n's and things, For the harmonic oscillator, we use the variable v for our integer counting number. X over alpha. I didn't give myself enough space. Let me rewrite this alpha over here. Alpha to the fourth equals h bar squared over nkf. E to the minus x squared alpha x squared over 2 alpha squared. So this ends up being the equations that work, and this is the reason why they use alpha to the fourth. So if you use alpha to the fourth, when it comes to the Hermite polynomials, you just end up with an alpha term rather than an alpha to the 1/2. If you were looking at the worksheet, it turns out the functions I gave you last time, when we were working on that worksheet a week ago and a little bit in our last class, I was giving you these functions. It didn't look like these functions yet, but I was giving you these functions. There's an equation for the normalization constant. There's an equation for the Hermite polynomials. And if you have some of the helpful wave functions and energy equations sheet that I passed out on the first day, it's given to you. Harmonic oscillator. All this stuff is given to you. They do this weird like yx substitution thing. I've just already substituted in because I know there's reasons for it, but when they do too many, like I'm simplifying things with redefining variables, it gives me a headache. So I didn't write this in terms of y, I just wrote it with y plugged in already. That's why it looks different than your equation sheet. And it gives you the Hermite polynomials and the generation equation for the Hermite polynomials, the normalization constant in terms of this v, all of those things. And I'm going to write them down as well. Again, so we can just kind of think about them. Our normalization constant depends on our counting number. And again, I think, awkwardly, normalization constant is not given on there. Probably because there's at some point going to be questions that ask you to find the normalization constants. But there is an equation that just gives us the normalization constant. It's 1 over alpha squared pi to the 1/4. And yes, there are ways to rewrite this, but this is the one that's simplest to me. 1 over 2 to the power of v, v factorial to the 1/2. So depending on our quantum number, this alpha squared out front, that's always the same. This 2 to the power of v, v factorial, that changes depending on which function we're looking at. The Gaussian part, that's always the same. Question?
Is the factorial only with the v? Or
Yes.
with
Yes. So it's like,
Thank you.
yeah, it's just with the v. It's not quantity to v factorial. Question?
I guess I'm still a little confused on the alpha to the fourth thing. Does that mean alpha is a fourth root of that formula?
Yeah.
Right there? Okay.
Yeah. If you look other places, it has it written as alpha equals fourth root of that stuff. For some reason, this made more sense to me when I was crunching through rearrangements last night. And it really does come down to just how we're rearranging all of these different parameters, this h bar, m, k, rearranging all of those things. People just choose to do it different ways. They end up with the same eventual answers. They all, like, everyone who does it all their different ways, like I honestly looked in 3 different books, they did it 3 different ways, and they all get to the same spot. If you plug in all of the definitions, all of their different definitions, you always get the same functions. Why they do it different ways, I don't know. Give me a big headache. So that's that. And then the Hermite polynomials, the interesting thing with these is it's actually a series that we can generate. So if we have, and I'm just going to write it like this, if we have h0 of x over alpha, and again, this is where they do that funny thing where they plug in y. I'm just going to keep it as x over alpha. It's just equal to 1. Right? So if we are looking at just the first answer to this, it just ends up looking like a Gaussian function. If we look at our first our second answer, H1, x over alpha. We get 2x over alpha. Then if we want to get our third answer, here's the neat thing that happens with this. And there's actually several different ways that you can get to generating these Hermite polynomials. A really cool way to do it that we're not going to do now, maybe we'll do it in future classes, is there are these things called ladder operators, which essentially push you up to a different function or take you down to a different function. So it's like going up rungs of a ladder or down rungs of a ladder. This is a really fascinating way to generate a series of answers. Taylor series expansions also do it. There's a bunch of different ways. But you end up with this situation where, I'll write it like this. H2 of x over alpha is going to be equal to 2 times x over L. Make sure I'm not messing this up. Minus right? You end up with this equation for H2 that depends on the two answers below it. And if we plug in everything for that, I'm going to switch back to flu for the H2. That's going to give us H2 of x over alpha. My alphas keep getting weird. Is equal to 4x over alpha squared minus 2. Do I have a typo there? Hang on a second. Should definitely be 4 minus 2. Hold on. Okay, I definitely have one type. No, I've got my minus sign.
I think it's
I agree. 2 times y. 4. Oh no, I'm okay. 4 minus 2. Because y is equal to 2, so that should give us 2 times 1. This v should definitely be here. Okay, I'm going to have to deal with that in a moment. I can't believe I didn't notice this last time. Let me check one more source real quick. It's bothering me. Yeah.
I think it's because it's v plus 1, and so v is like actually v minus 1 for us. So it would just be 1.
In which one? Okay. Here?
Yeah, I think
This
that would
v?
be v minus 1, because on the equation sheet, it's like v plus 1. And then
Oh, right. Yes. Okay, yeah, so that's just equal to 1. Okay. I shouldn't have put that v in. How do I want to do that? Let's leave that v there for a moment. I know, you're exactly right. I'm gonna put it as times 1 right now, and we'll explain what that times 1 is in a moment. Yes, you're completely correct. Thank you for finding that. It was driving me up the wall. We can do the same thing for H3. And we get this kind of generation thing. We start to notice a pattern. H3 of x over alpha is equal to, I was going to have another. Is equal to 2x over alpha H2 x over alpha minus 2 times 2 times H1 x over alpha. Right, so again, we notice this pattern of the third answer depends on the second and the first. Sorry, H3 depends on H2 and H1. Right, so it's the two answers before it can be used to generate the third answer. When we plug in all of our definitions for this, we get we end up with that equation for H3. And you'll notice even answer, odd answer, even answer, odd answer. Each one ends up with an additional kind of even or odd term. And there's a generic equation we can use. It is on the equation sheet. That is the H of the V plus 1, so the next answer up. So if I wanted to find H4, that would be like H3 plus 1. That would be equal to the answer before H4, which would be HV, minus the answer that's 2 above it. So this makes it so as long as you know the first two answers, you can generate as long as you know answer 0 and answer 1, you can generate 2. As long as you know 1 and 2, you can generate 3. As long as you know 2 and 3, you can generate 4. If you know 3 and 4, you can generate 5. If you know 4 and 5, you can generate 6. So on and so on and so on. And you end up with this kind of endless series of functions that you can generate, not dissimilar from what we saw with the particle in a box, where the particle in a box had an infinite number of answers, right? We had n goes to infinity. Here we end up with the same situation. This counting number v can keep going up and up and up. Does anyone notice the really weird different thing between this and what we saw before? What was our smallest n value for the particle in a box? What's our smallest v value here? We can actually have v equals 0, right? We can have this lower number. It has to do with the boundary conditions. Again, we didn't solve this thing out, but it has to do with the boundary conditions applied to this Hamiltonian. But it ends up that there is some v0 answer. So there's that possibility for a v0 answer. Okay, so once we have our wave function, we've got the normalization constant. That's an equation that's kind of strange. We got our Hermite polynomials, also equations that are kind of strange. We got our Gaussian function. Hopefully it will not be too strange to you by the end of the quarter. Gaussian functions are fantastic. All of these functions are fantastic, but Gaussians in particular keep coming back. Once we have our wave, so that's our answer. Those are the wave functions. We can do some, amount of logical consideration for why these answers work. The same way we said, hey, we can see that there's this like x squared term, so the Gaussian makes sense. We can go through these different polynomials and kind of make sense of them. We've already done some of that work in the worksheet that you had where you're just doing the mathematical processing. We've already shown that these things are orthogonal to each other in that worksheet. We've already done generating some of these normalization constants on that worksheet. Right? And if we start to notice, this is a difficult pattern to notice if you just do 3 of them. But if on that worksheet I had you, instead of doing the first 3, if I had you do the first 8, you might have noticed the pattern better. I wasn't going to do that to you, though. I'm just going to tell you. Now we can go and do our typical things. We've got our normalization. We can show that they're orthogonal, and we can start calculating the energies associated with them. And we get a nice energy associated with this. Here we go. Right, so with this wave function, I actually want to put this here as well. I'll write it on the other board as well. But we end up with an energy of, this problem with that counting number v is equal to v plus 1/2 h bar omega. Right, that becomes our energy associated with this. Two things to notice. The physicality of the problem is buried in that omega, right? The mass of our oscillator and the spring constant, that restorative force constant, those are both buried inside of omega. So depending on how stiff or loose that spring is, how strong or weak that bond is, that will change that vibrational frequency. And that will change our resulting energy levels. The other interesting thing here is when we have our V equals 0, the energy is not 0. That's an important feature. You know, if we ended up with 0 energy, that'd be like the particle doesn't exist. That was why in the particle in a box, we couldn't have n equals 0 because then our energy would crash out to 0. In this case, with this extra term and these boundary conditions, we end up with a V plus a half. Now that V value could be 0, and we still would have something existing there. We'd still have some vibration, some interaction. Now, this has all been for thing attached to wall. Which is not that interesting. Right? That's not what particles really look like. So I want to show you how we can extend this to talk about molecules. But are there questions about this yet? Yeah.
Is there like a reason why it's V plus 1/2?
Yeah. Is it easy for me to get to that with like these mathematics? No, but what we can do, and I think there's some homework assignments.
It's not significant.
What's that?
I was just wondering if it's.
No, it's super important. But like why it ends up like this is really difficult to derive from just having the Schrödinger equation. Once we have the answers, it's pretty easy to calculate that. But remember, we generated these answers from solving the Schrödinger equation, which guaranteed us that these were going to be the energies. Essentially, what it comes down to is this equation, we have to essentially do Taylor series expansions to get that term, that 1/2 term, right? Go through the entire process to figure out why this ends up being the energy. And so the reason I kind of was like, yeah, is because I don't want you to do that.
Okay.
I think it's really interesting. I think it's a really great exercise. But that's something you do if you did a graduate level quantum mechanics class. Question over here.
I think it's almost the same question, but so are we expecting to derive that E sub V, or are you
No. Right? That E sub V is given on your wave functions and energies equation. You'll never be asked to derive that one. For the particle in a box, I think you could be able to derive that one. The harmonic oscillator one, no, that would be difficult to derive, so I wouldn't ask you to derive that. Can it be derived? Yeah, it can be. It's beyond the scope of this class. Other questions? Yeah?
How come it's 12 in front for the second term for H of 3?
Did I have a typo? I think it's 12. We've got 2 times 2 times 4. Ooh. Let me see. H1, 2 times 2 times 2. That should be 6. It is definitely 12. I'll have to double check that. I know it's 12. I'm back to like, ooh, did I make a typo someplace? I don't think I made a typo. H3 is 2 times 2 times H1, which is 4x squared.
Is it because the -2 from
H1. Say again?
Is it because the -2 from the H2?
It could be. I would have to do out all of the math step by step to make sure. I know the 12 is supposed to be there. I would have to do the math slower to make sure I did that correct. I know it's correct, but I didn't do the math slow enough to show all the steps to why it ends up being 12. Other questions? Okay. Let me show you one more thing real quickly, and then we'll get to the quiz. That is for 2 masses. So if we do 2 masses, we have this type of setup. That would be our L naught. We could have some displacement of L2. We could have some displacement of L1. And we just, again, we do the same thing we did earlier where we just kind of redefine that displacement idea into a constant or into a variable. So we're going to have x is equal to L1 minus L2 minus L0. Right, so the total amount that the spring gets stretched or compressed, essentially. And then we define a second thing to deal with the fact that we have two masses. It's referred to, we use the Greek letter mu, the lowercase mu for it. And this is the reduced mass. And it's just going to be m1 times m2 over m1 plus m2. And after we define those two things, we just kind of go through the whole same problem again with these new things. All of our masses get replaced by mu. So our Hamiltonian changes slightly. Our Hamiltonian ends up being negative h bar squared over 2 reduced mass rather than just m1. D by dx squared on psi plus 1/2 kx squared on psi equals e psi. We define a omega slightly differently as the square root of k over reduced mass. And then just pretty much any place where you see an m, you replace it with this reduced mass. And this x term, we still define everything in terms of x, but our x is defined slightly differently. After we do that, everything else kind of comes out the same way. That's what was off. Our energy ends up having the same equation associated with it. Our energy ends up having the same equation associated with it, but the omega has a slightly different meaning to it. That's where the physicality of the problem is hidden again. Our wave functions all look the same. Our alpha, this m just becomes a reduced mass, and you end up with the exact same thing, right? Our alpha to the 4th ends up equaling h bar squared over reduced mass, force constant. And then everything else comes out the same after we do that slight redefinition. Works out really well. I'm going to stop there. Oh, questions? Yes?
Are you like, with this, are you trying to say like bonds or kind of like springs?
Yeah.
Okay.
Right. So, or springs are like bonds, which way you want to think about it. I always think about bonds first because chemistry, right? Why do springs act like springs? Bonds, right? That's me being cheap, but it's a matter of priority, right? Essentially what we're saying is when you've got two nuclei with electrons kind of being shared between them, pulling them away from each other has a restorative force. It tries to pull them back to equilibrium. And that restorative force, whether we call it a spring or or like a pendulum or an oscillator, is that restorative force. And that's what's happening in the bonds. And so it turns out we can model some bonds like this, and I'll have to pick that up next time because I want to leave enough time for the quiz. Other question? I think it would work out the same way. This is just we have to pick a coordinate system, and really what matters is how far are we away from this L0 totally. Other questions? Yeah.
It's distributed out.
Ah, yes. Okay. Yeah. Because this whole thing gets multiplied through. Yes, there it is. Okay. Thank you. Okay. Other questions? Thanks for noticing that. I was sure it was that. Okay. I'm gonna go ahead and